Hello everyone. This video covers section 10.3 chi-square test. There are actually many chi-square tests. We only want to focus on one here, a test that has to do with contingency tables, and more specifically, the one we're going to deal with is called chi-square test for independence. That's the one we're going to focus on. Now, in case you forgot what a contingency table is, we saw this in chapter 4. Remember, a contingency table is something that looks like this, where you have rows and columns. And we use this in chapter 4 for probability. Remember, for example, this was Republican, Democrat, Independent, Other. This was Muslim, Christian, and Jewish, and so forth. Okay? So in this particular case, we have 3 rows, and you have four columns. Okay? So this is another hypothesis test, which means you need to have a claim. The claim is always going to be this: the row and column variables, which in this case will be these variables and these ones, are independent, and the alternative is that the row and column variables are dependent. That's what we're going to be testing. Okay? The part that takes a while to compute by hand, the calculator can actually do this, but it has to be a TI 8084. 83 cannot do this anymore. To do this by hand takes a little bit of time, but it's not a long time. So you don't have a TI 83, it's not a big deal. You still can do it by hand. It will not take that long. All right, so this is the thing you have to be careful. You want to have 2 values you have to worry about. O means observe, and this is always given because that's the data. E means expected, and most of the time you have to find these values. This is actually the formula to find them, which is pretty easy, but it's pretty time consuming, like you will see in a little bit. Then in step 3, just as before, you had 2 choices. You're going to find the rejection region or the p-value. This test is a one-tail test, which means you only have to worry about one side. In fact, all you have to do is find chi-square right. Just be careful because here alpha is not divided by 2. And to find the p-value, remember you have 2 choices. You can use the calculator, which in this case, this will be chi-square CDF. From chi-square star to 1000, and then the degrees of freedom. Or you can use the table to approximate the p-value, just like we did before. Okay. Now, the part that is new also is how you find the degrees of freedom. The degrees of freedom is going to be the number of rows minus 1 times the number of columns minus 1. So for example, let's say that this was the actual problem, where notice there is 2 rows and there is 4 columns. So if this was the case, then the degrees of freedom will be 3 minus 1 times 4 minus 1. It will be 2 times 3, and it's 6. So this is how you're going to find the degrees of freedom, which is different than before, but it's still pretty simple. And then finally, as usual, the conclusion, which remember there is only 2 choices. All alone is either reject HO or fail to reject HO. Remember, this implies that row and column variables are dependent, because if you reject this, then automatically this is true. And fail to reject implies the row and column variables are independent, or that you don't have enough evidence to reject that they are independent. Okay, let's do an example. The question says this: according to a political analyst, the female population in HT town tends to vote Republican. So pretty much the person is claiming that being Republican implies that you're going to be female or the other way around. So therefore the person is implying that the two variables, that the row and the column variables, are dependent. Now, regardless of what it says, you're always going to do this for the step one. You're going to say row and column variables are independent. So that's going to be the claim all the time. And then the alternative is that row and column variables are dependent. Even though the claim that the analyst is making is that the row and the column variables are dependent. We'll get to that in a little bit. Remember, this is also how you know you have to do hypothesis testing. Anytime that it says, is there enough evidence? Okay? Now, how many rows you have? 2 rows, and you have also 2 columns, which is the smallest number you can have. The smallest you can have is 2 by 2. Now here you have 4 expected values. So this is O, so is this, and so is this, and so is this. So you have 4 values. The ones you don't have are the expected values. So the first thing you need to do, just like in chapter 4, is add the rows and the columns. So this is 40, this is 60, and the total is 100. Then add the rows also. So this is 50 and 50. Okay. The next thing we had to figure out is what is the value for E. Now you have 4 observed values, so therefore you need 4 expected values. To find expected values, like you will see right now, is very simple, but it can be time consuming. Now, look to the number 10. So let's focus on number 10. This is technically in row number 1 and in column number 1. So therefore, just for notational purposes, I'm going to say E11. So the 1 means row 1 and column 1. Okay? So this is how you're going to find the expected value that goes along with this. The sum of row 1 is 50. So I'm just using the formula from the last page. So this will be 50. So this is the sum of row 1. Then the sum of column 1 is 40. And the total sum is 100. When you simplify this is equals to 20. So that's how easy it is to find expected values. The issue is that you're going to have to do this 4 times. And you have 20 of these, you'll have to do it 20 times. Once you have done that, then in parentheses, you should put the value we just found. So we found this to be 20. So this will be now the expected value. So then let's move to the next one, to the number 40. 40 you can see is in the first row, but it's in the second column. So therefore we're gonna call this E, row 1, column 2. Now again, the sum of this row is 50. The sum of the second column now is 60. And the total sum is 100 again. And this is equal to 30 now. So therefore, in parentheses, just put the value there, and this will be 30. So this is the associated expected value corresponding to this observed value. You have to do this 2 more times, but in this particular case, the answer is going to be exactly the same, 20 and 30. And the only reason is if you try to find E21, this sum is exactly the same, and this sum is exactly the same. So therefore, it will give you again just 20. Same thing for this one. So once you find the expected values, now you can complete step 2. So all you have to do is plug it in this formula, and notice that you have 4 observed values and you have 4 expected values, so you have to do this 4 times. So this will be 20 minus 10 square over 20. Why? Because remember, the first observed value was 20. The first expected value is 20. The first observed value is 10. So you just literally plug it in. Then move to the next one. So now this will be 30 minus 40 square over 30. And so forth. So you have to do this 4 times. And then finally, 30 minus 20 square over 30. On the top, it actually doesn't matter if you have E minus O or O minus E, because when you square, it becomes positive. But in the bottom, you have to make sure that the denominator is E. So be careful with that. Then simplify all of this, and you end up with something close to 16.67. Sorry. Once you have the expected value and the observed value, you can actually use the TI-84. The 83 doesn't really do this, and you have to go to Stat, Test, and then you have to pick chi-square G of F, which means goodness of fit. And then in one column, you put the observed values, and the second column, just put the expected values, and it will give you this value automatically. You just have to be very careful to enter all the values. I'll show you that on the next example. But if you don't have a TI-84, it's fine. You can just do it by hand. Right. Then for step 3, remember, we need to find the rejection region. And remember that this is a one-tailed test, which means you only use alpha. You don't do alpha over 2. So and then this will be chi-square of 0.05, because alpha was given to be 0.05 right here. And remember, the degrees of freedom is the number of rows minus 1 times the number of columns minus 1, which is 1 times 1 and 1, which is the smallest number you can get for degrees of freedom. So this is equals to 1. Then you look to the table, this is 3.841. Then, just like before, you have to draw the rejection region. Remember that this is not symmetrical. The rejection region is 3.841. So anything in here will be rejected. So this is the rejection region. And this will be the fail to reject HO. Well, clearly chi-square star, which remember this is the same thing as chi-square right, is on the rejection region. So therefore the conclusion will be to reject HO, which means row and column variables are dependent. Now, if you remember, that was exactly what the political analysts claim. Show you again. According to a political analyst, the female population tends to vote Republican. So the analyst is claiming that female and Republican are dependent. So the analyst is claiming that these variables are dependent on this one. That's exactly what we just showed right now. So therefore, that means that there is enough evidence to support the political political analyst claim that females tend to vote Republican in that town. Republican political analyst. And that's it. All right, what about the p-value? All right, so for the p-value, let's do the calculator first. For the p-value method, remember that step 1 and step 2 are exactly the same. So let's do the calculator first. So we do the calculator. The p-value, remember, is the probability that chi squared is greater than chi squared star, which in this case is the probability that chi squared will be greater than 16.67. So we use the calculator. It will be chi squared CDF. The lower bound is 16.67. The upper bound is 1,000. And the degrees of freedom is 1. And this is around 0.000044. Remember that to access this, you need to do a second variables, and then just look for chi squared CDF. Okay? So that's a p-value, which is step 3. For step 4, we compare the p-value, which is 0.000044, with alpha, which is 0.05. So clearly this is less. And remember, less means reject HO, which is the exact same conclusion. Now let's do this using the table, just in case you don't have a fancy calculator. So we use the table. Remember that the table only gives you an approximation, but that's all you need. So we use the table. We still need to find the probability that chi squared is greater than 16.67. That's not going to change. Then look at the table, and we're trying to find 16.67. Remember that you only have 1 degree of freedom, or 1 degree of freedom. So therefore, 1 degree of freedom is this. And the value we're trying to find is 16.67. And we went over this in chapter A. You can see how the value for alpha keeps getting smaller when the number increases. The number you want is 16.67, which is bigger than the last value. And if you are in this side, all you have to do is pick 0.0001. That's it. So that's an approximation, but that will do for what you're trying to do. So then you say, well, the p-value will be approximately equals to 0.001. So remember, you don't have to multiply by 2 because this is not 2 tails. So this will be the answer to step 3. Then step 4, the p-value is 0.001. Alpha was 0.05. or 0.50, so clearly this is less, and again the conclusion is reject HO. So therefore, you have 2 choices. You can use the calculator, or you can use the table. Both of them will give you the same conclusion. This is supposed to be the exact answer, and this is just an approximation, but both of them give you the same conclusion, which is what you want. The table is actually a little bit faster once you get used to, but you had the choice to use this one or this one. All right, well, you didn't understand the last one. Here's your last chance to redeem your sins. So let's do another example. The question says, an instructor wishes to see if the way people obtain information is independent of the educational background. So you have a survey between college students, high school students, and to see if they use TV, newspapers, or other, which other should be the internet in these days. But anyways, so here, remember the claim, regardless of what the question says, is going to be the same. Row and column variables are independent, and the alternative is row and column variables are dependent. This problem has the number of rows is 3, and the number of rows is 2, and the number of columns is 3. And in this case, I already give you the expected values too, in addition to the observed values. Remember, the observed values always have to be given. Now, if you have a question on the test, it will be like this, where you already have the expected values given. Or I mean, if you had to complete a whole problem, this will be given, so that will make the problem way faster. Okay. So once you have the expected value and the observed values, all you have to do is plug it into this formula. So these are the first two values. Remember, it's the expected value, which is 36, minus the observed value, which is 20, divided by expected value. In this particular case, you have to do this 1, 2, 3, 4, 5, 6 times. So if we keep doing this, the last one is going to be 38 minus 50 squared over 38. Make sure that you square the values. And once you do all of this and simplify everything, and you should check this, this is around 27.07 or something close to this. Like I mentioned before, if you don't want to do this by hand and you have a TI-83, these are the commands. You go to first stat and then go to edit. So you need to enter all the information. So you have L1 and L2. Make sure you clear this so you can put the data. And here you will have the observed values, which will be 20, 30, 50, 60, 40, and then 50. And then the expected values, which are 36, 32, 32, 44, 38, 38. And then go back to stat, and then chi-square g of f, and just follow the commands, and it will give you this value as well as the p-value at the same time. All right. Now, you don't have one of those calculators, that's fine. You can just compute the value like this. The problem won't get any longer than this, so it doesn't take too long. It's not that short, but it doesn't take that long. Now, remember, for the step 3, you need to find the rejection region, which is equals to chi-square of alpha. Remember, alpha is not divided by 2, with the degrees of freedom. Remember that the degrees of freedom is equals to the number of rows minus 1 times the number of columns minus 1, which in this case is equals to 2. So therefore the rejection region will be chi-square of 0.05, because alpha is 0.05, and the degrees of freedom is now 2 from here. And you look to the table, this is 5.991. Then draw the rejection region, where this one starts in 0. It keeps going forever. So now we have 5.991. So if it is here, it will be rejected. And if it is here, it will be failed to reject HO. Alright, so what's the value for chi-square star? Is 27.07, which is clearly in the rejection region. So the conclusion is to reject HO, which again implies that the row and column variables are dependent, and that's it. If you want to find the p-value, Remember that we have two choices. You can just use the calculator first, so let's do that one, or you can use the table. So for the p-value, remember the p-value for step 3, it will be the probability that chi squared is greater than chi squared star, or in this case the probability that chi squared is greater than 27.07. Then you go to second variables. This will be chi squared CDF. The lower bound is 27.07. The upper bound is 1,000. And then the degrees of freedom is 2. And this is around 0.00000 is 1, 2, 3, 4, 5 zeros, and then 1, 3, 4. Okay. Remember the graph looks like this. Just for the record, this is 27.07. So this is the lower bound, and the upper bound is 1,000, and so forth. Right, so remember the last thing you do, you compare the p-value, which is this. Clearly this is less than alpha, which is just 0.05, and that implies to reject HO. And N of the study. Now, if you want to use the table, just like we did in the very last example, if you look to the table to approximate this probability, this number is bigger than the last one on the table, and if this is bigger than the last one on the table, remember you can just go with 0.001. That's all you need. So therefore the last part you do is the p-value is 0.001, which, remember, this is just an approximation. That's all you need, because clearly this is less than alpha, which is 0.05, and that again implies to reject HO. And that's it.